All right, so in this case, we're trying to find out an approximate value for delta H, which is the heat of reaction. And all we're given is the information is how much enthalpy is in each bond. Now, this won't give us an exact value, but it's a pretty good estimate. So the way we start this is by sort of sketching out the Lewis structures of each of these. So without getting into too much detail, NH3, remember N likes to form 3 bonds. So NH3 is going to look like this, NH3. And if I complete this, there will be some dots here. We're not going to get into that too much right now. But this is what NH3 looks like. And there are 2 of them. So I'm going to draw this twice. You don't always have to, but just for the purposes of this. N2 is N triple bonded to itself. Again, N usually likes to form 3 bonds, and we can talk about how this forms, but for now I'm just going to assume we know that. And then 3 H2s. So 3 H2s. All right, and so this on the left is what was there before. On the right, that is what is thereafter. So in order to make this work, we have NH3 to begin with. We have to invest energy to break all these bonds, because these bonds are in the way of forming new things. So I got to break 6 NH bonds, if you count them up, and NH bonds have an enthalpy of 391. So that is an energy investment. So we need to invest 391 kilojoules times 6, because there are 6 bonds we're breaking. And you can think of it as kilojoules per mole times 6 moles. 6 moles of bonds, because we always think about this in terms of moles of molecules, not really single molecules. But either way, 391 times 6 is what we're going to have to do there. That's our investment aspect of things. Now on the other side of the reaction, we have a few other bonds. We need to form these bonds. And when you form bonds, energy is not absorbed, it's actually going to be released. So in this case, we are forming a N-N triple bond, which is 946. So, and there's only one of them, so we're going to get that back. So while these were investing, that's positive energy, this is going to be released, because when bonds form, they become more stable, and so it's negative 946 kilojoules. And technically it's kilojoules per mole times 1 mole, but we get the idea. And then we're also going to form 3 HH bonds. So we're going to get back 436 kilojoules times 3 of these bonds. And so now we're just going to calculate this. So 391 times 6. On this end, we're investing 2346 kilojoules. That's positive, that's energy going into breaking the bonds. Here we've got negative 946 for this one, and then 436 times 3 for the hydrogen. Here we're getting back negative 1308. I'm going to add that to my 946. So I'm getting back 2254 kilojoules. So I'm investing 2346, I'm getting back 2254. And so that's actually, if we do this, we're still going to end up with a positive delta H, because we're not getting back as much as we put in. We're going to get a plus 92 kilojoules. Now in money, we always like positive amounts, but for energy, we usually like negative energy. We would like things to become more stable. So delta H for this particular reaction would be positive 92 kilojoules. And this is not exact. If we actually look it up, it will probably be close to this, but not quite. But that is how you estimate the enthalpy of a reaction with these bond enthalpies. And normally you'll have a chart of these to look up. You're not going to usually have them nicely cherry-picked for you. And you got to be careful. There's another bond, an N-N double bond, which has a different enthalpy. So this is a triple bond one, which is what is forming here. So until next time, I am Derek Genova. Have a delightful day.